So we know about two level converters where you have a plus VDC or minus VDC. So that was what the two level full bridge converter we have or DCSC inverter. We knows that okay they are used for very small power up to uh, up to 50 kilowatt. And if you want to go for a higher rated power supply, then you have to add two in parallel. In that way, you will know that how it is the this converters is used. That is mainly two level converter, DC AC inverters. Okay, that inverters you know. So that is called the two level. You will get plus VDC or minus VDC. So it is very good for low power applications. But when you go for a high power application, then you have to you have to choose for the multi-level converters, which is today very popular actually. It is very popular in the industrial applications, especially from megawatt drive to today also the small power supplies also we use that one. So today we will discuss this multi-level converters, and after finishing this then we will start the phase controller, because once the introduction is over then we will go to phase controllers. The overview of the phase controller already I have recorded and I put in the YouTube also. So I will send the link where you can access to that lecture. Those who have not attended the first and second class, okay. For them, I will put again. Today I will send in the WhatsApp group, and in the WhatsApp group you can add those who joined today. If you will send your mm, mobile number, I will put into that group, or Saurav can put also. Okay. So multi-level converter is more than two level, is a multi-level. So multi-level means what we get actually. So two level, it is a kind of square wave, pulse PWM square wave. Okay, small pulses in the form of a square wave. So square wave, what you get, if you see this square wave, a simple square wave, you will find you have a third harmonic, fifth harmonic, all odd harmonic it is present in a square wave. If you take the Fourier analysis of that one, it is all kind of harmonics are present there. So just you come to a sawtooth wave, the quasi square wave. So quasi square wave, I think you must be knowing this is some kind of like this is called the quasi square wave. Oh, sorry. It is not after. So this is called this quasi square wave. So this quasi square wave, when you find out the Fourier transform, you will find that third harmonic and multiple of 3 are absent here. Okay. So this is nothing but VDC 0 and minus 3 level is coming in a quasi square wave, where the third harmonic component are absent in this. Similarly, when you have a multi-level converter, more than one level in the output voltage, it will be going towards a sinusoidal wave. As a multi-level, if you have more number of levels in the output voltage, it will be like a, for example, you have a plus VDC minus VDC. This was the, this is our plus VDC minus VDC. If you see here, this one, it contains all kind of harmonics. When you go a little bit, for example, plus, minus, again plus, like a quasi square, you see that third harmonic is present, absent here. Third and multiple of 3 are absent. When you go for like the staircase, okay, like this. Okay. So like this, if you see like this waveform, you can see that it is nearly approaching like a sine wave. And this is the purpose of because when you have a like this, you need a filter circuit. You need a large filter circuit, inductor, capacitor, this type of LCL. So similarly for this also. But when it is like this, you have a higher level, then this filter requirement is not there. And that is what this filter requirement, when this you are in the higher level, then filter requirement will be minimal, so that your converter efficiency, other thing will be improved. That's why today all kinds of high power drives in terms of megawatts, starting from Indian Railway big engine up to 6,000 HP, one traction motor is having 6,000 HP power. So those type of power, when you have, you will design a filter for that drive. It's a huge, very large filter it is required. And in the train, in the engine, within that space, you cannot accommodate such a large filter circuit. So when you go for higher level of the voltage, then this filter requirement is nearly zero. And this is what the multi-level converter. And multi-level converter is more than 3 level, and we will see some design aspect also, because in power electronics, design is more important than our hardware analysis. So here this advantage of multi-level is a higher power, higher voltage, like all kind of transmission system today, HVDC, high voltage DC, everywhere we are trying to use all the multi-level, high power and high voltage application. And it's synthesized to higher voltage. For example, if you have a low cost device can be used for a higher voltage, because two low power device can be connected in series, so that the reverse recovery voltage, okay, or inverse voltage, it can block higher reverse voltage, and that way your cost will be come down because you use low power device. And as the number of levels increase, so THD also decrease. Okay, as number of the level. And that is what the multi-level inverter offers better performance at low switching. As the switching frequency is low, your power loss in the converter is directly proportional to switching frequency. As the frequency is low with same performance, you get higher efficiency. And then the PWM technique, which is okay, this the voltage stress is VDC by M minus 1, where M is the number of level. And number of level increases, your voltage across the switch decreases. VDC divided by that. So that is why when you have like this, so for example, you will have the dV by dC. What is that stress? I have already told you when we studied the thyristor circuit. So dV by dt will occur when the thyristor is turned off. In the turn on, di by dt protection is required in a thyristor. Okay, di by dt when you turn on, and dV by dt when you off the thyristor. When you off thyristor. So when you switch off the thyristor, you experience this dV. So what is this dV by dt? You see, this dV by dt in case of an inverter is that when you have a switch, for example, a bidirectional switch I have here, and this switch I am having switch, this is a bidirectional switch. So this dV by dt, when I want to apply a voltage like this, for example, plus and minus. So if you see here, what is the change in voltage? Change in voltage is plus VDC to minus VDC. Okay. And when you have a quasi square, for example, like this, that means you have VDC by 2, okay, to 0 to minus VDC by 2. So less stress as compared to this one. If you have 3 level, you will see that it is 1/3 of VDC, 2/3 of VDC, VDC. That means your stress of dV by dt, change in dV by dt across the switch is reduced. Why? Because if you have a sudden change in the dV by dt, in case of thyristors, we have already studied this one, VI characteristics of the thyristor. This is my current, this is my voltage. And initially, when you don't apply gate pulse, you will see that it will follow, okay, some. So this voltage is a breakover voltage, okay. This breakover voltage means at this voltage, you have a PN, for example, IGBT or thyristor. There are 4-layer device, PN junction. And in the junction, what it will create? It will create local hotspot. So you have a like this, PN1, PN, PN. So this is one junction, J1, J2, J3. So this is the main blocking layer. So what will happen? In this layer, the charge will flow immediately, which in turn will create a local hotspot here. Local hotspot will not known to you, but it will damage the switch immediately. That is why this dV by dt protection is a big literature, big study. In case of if you just put in IEEE transaction and just search dV by dt protection, you will find millions of circuits people have developed for this, because it is very important in the for the switches to protect the switches as well as to increase the reliability of the system. Okay, that is why these are the few advantages. And we will see the diode clamp 3-level inverter. Okay, I have just drawn 3-level inverter, and multi-level are available also, 5-level, 7-level, up to 59 level till today people have developed. Okay, they have already, it is already developed up to 59 level. So this is how our converter circuits are. And now this is a 3-level. 3-level in 2-level. This is a 2-level converter. Okay, you must have studied 3-phase 2-level converter. So this is a 2-level. Okay, VSI, 2-level voltage source inverter. Okay, and it is connected to DC link voltage. Now it is a 3-level converter, and in 3-level converter you can see this 4 switches in a leg. Okay, these 4 switches are connected. Okay, M minus 1 is the number of level. If you have one leg is having 4 switches, M minus 1 level you will get. So this is 3-level. And then you know here there are 2 diodes which is connected here in the midpoint between 2 switches, 2 IGBTs. This is connected, and this is connected to this neutral point. These 2 capacitors which is connected parallel, and this is called the neutral point, and that is this, these diodes are connected to this neutral point. So when these are connected to the neutral point, that is why it is called the diodes are connected to the neutral point, okay, and clamped to the neutral point. These diodes are clamped to the neutral point. That's why this name is a diode clamp. The diodes are clamped to the neutral point, okay. That's why the name of this converter, this multi-level inverter, is diode clamped three-level inverter. And another name, because it is clamped to the neutral point, sometimes we call neutral clamped also. Neutral clamped, neutral point clamped inverter. Okay, point clamped VSI. Okay, so this name is, you can see here, in this case, it is very beautiful. Actually, when the operation you will know that you see this switch and this switch both are complementary, and this switch and this switch both are complementary. S2, S4, and S1, S3, they both are complementary. So any other time, any time, if this will not never be short circuited. Okay, first thing. Second thing, when you turn on these two switches, okay, maybe I'll put another color. So try to understand. This is very fundamental. When you turn on these two switches, so R and M voltage will be VDC by 2 by 2, as the input voltage is VDC by 2. Okay. Now, when this R is connected, when these two switches are on, maybe I should remove this. Okay. So when the lower two switches are on, these two switches are on, you see Rm, this voltage is minus VDC by 2. This is minus VDC. Okay. And when this is connected, when this only one switch S3 is connected, let's take the current is negative. So the current flows from R through this load through S3, and if this is off, this will be bypassed through this diode to this neutral point. And when this is clamped, you see what is the voltage? Voltage here is 0. So Rm voltage will be 0. So when, or if the current is positive, for example, if the current is positive, then current will flow from D1, okay, like this, through this to the load. When the current is positive, the D1 will conduct. When the current is negative, D2 will conduct. Because I already told you in your inverter circuit VSI that as a design engineer, we have preference to control the voltage, not the load. Load depend on the all our customers. What kind of load they will connect, that is depend on their choice, not your choice. That is why in VSI, voltage you can control, current is not in your hand. That is why we have a reverse bidirectional switch. All switches are bidirectional. Voltage may be positive and current may be negative also. So that is what this multi-level that you get when upper two switch are on, you get plus. When lower two switch are on, you will get minus VDC. When any of this diode clamp, whether positive and negative current, any of the diode they conduct, that is you will get the zero voltage. And that is how this is a three level inverter. Okay. So if you have any doubt in the middle, just clarify, because we are going to design these multi-levels. We will not do with the two-level converters. Okay, we will use multi-level converters for all our design aspect. So that is because it is transmission line, and we handle 400 kV and 100 megawatt, 400 megawatt. So the multi-level converters are prepared. Yeah. Okay. So this is what I have explained already, that for one phase, the when SA is 1, SA1 means SA1, SA2 are on, and SA uh, SA is 0. That means middle switches are on. Okay, the middle two switch SA3, SA4 are on, and D1 will and D2 will conduct depend on the current, load current, polarity of the load, positive or negative. Similarly, these lower two switches are on minus. So these are the three level. Okay. So this way, so what is the diode clamp thing is that the this is low voltage rating of active device, unequal duty, unequal high voltage, capacitor voltage unbalance is another problem. That means, for example, you charge these two capacitor, this capacitor and series, and you charge this maybe VDC by 10, and this is VDC by 2. So like this, it may charge because the internal resistance, or ESR, electrostatic resistance of the capacitor, it is unknown to us. And how in simulation you will never get the this unbalance, because simulation it is always perfect. When you go for hardware, you will see that this converters, what here the this device, where this DC will charge very high or sometime very low, and this will charge very high and very low. So the balancing of these two capacitors is a very important factor today. So that is another problem. So we are not going in detail to that one. And this is a three-level inverter, and you can see that we have a five level inverter here: one, two, three, four, 5 level. So 5 level inverters, this one. You can see that this is VDC by 2, VDC by 4, okay, and this is minus VDC by 4 and VDC by 2. And these are the clamping between 1 and 4, then 2 and 3, then 3 and 1. So like that. So when you will get here, you will get VDC by 2, VDC by 4, 0, again VDC by 4, and this way you can easily understand, you can find out that as number of levels you increase, you will see that it is coming nearly sinusoidal. It is approaching like a sinusoidal wave. You can see here. This is approaching like a sinusoidal. So this way, this is a diode bridge and diode clamp multi-level inverter. And what is the problem? You see here, when you have many these capacitors are connected in series, you see all the capacitor is not properly charging. One capacitor is charging very high, it is going up. Another is also charging towards very low, and another one is somewhat. That means all the capacitor has different electrostatic resistance, and that is why they charge differently. How to equalize this one is one of the biggest problem today in case of the diode clamp converter. But nowadays we are there is how to design when your design is perfect, it will nearly equal, it will charge properly. So I will tell in the last section what is the design aspect of this one. Okay. Now, this is a flying capacitor. Okay. So flying capacitor means this is my DC voltage, and instead of the diode clamp, we used to have a diode, we put a flying capacitor. So this capacitor we put as a clamping diode. Like clamping diode, it was connected to neutral point, but this is clamped to this voltage VDC by 2, VDC by 2, like that. This is clamped. So how this is takes place when this is connected 1 and 2. So you see your this one is the circuit 1 2 connected. This is your, and when your S1 is off. So what will if you have a positive current, okay? So then this will flow the current like this. And if you have a negative current, okay, and this will charge this capacitor through this S2, and this will discharge your capacitor from. So this is what you're discharging, and this is what you're charging. And this way, you can easily control the similar kind of control for these 3-level flying capacitors. So what is then when S1, S2 are on, you get VDC by 2, what we have already discussed. And then uh, when S1 and S2, if one S3 and S1 is on, so because it is clamped to that voltage, so it became Rm became 0. And when SA, SA1 and SA3, 3, 2 and 4 are on, so then you get 0, and lower to switch you get minus, okay, minus VDC by 2. So this way we can control this capacitor clamp. And one problem in this capacitor clamp converter that you require to charge this voltage, the capacitor. Initial charge you must charge up to VDC by 2. If you don't charge, it will draw large amount of the charging current, which may damage your switches. And second one, capacitor voltage unbalance, because you have so many capacitors, they always there is a different ESR, electrostatic resistance, so they will charge differently. So that is why it is a very, very, this is only used in the applications for the reactive power exchange. Especially this flying capacitor is very popular in the fax device and reactive power control. Okay. And in the reactive power control, you don't require to balance the voltage. If you have a motor drive, if your voltage are not balanced, then you will see that motor will generate a vibration, motor will create a vibration. And this way, flying capacitor, your S1, S2 are on, then VAN is your plus VDC, and then S1 is on, and S2 is off. You get 0. Okay, S1 on and S2 off because this plus VDC, okay, this. And then S2, similarly you can, this S1, S2 you can understand, you can put. So NC means no change in the state, but output will remain as it is, charging and discharging, okay. So I already told when this lower switch is on, this is charging. When upper switch is on, it is discharging. So there are how many capacitors are required? N minus 1 into n minus 2 divided by 2, and this is the voltage, the innermost capacitor clamped voltage is VDC by n minus 1. So this is the just fundamental. And similarly, n level also you can go for the n level of the multi-level the flying capacitor. So VAN is S1 and this. So this way you can you can derive this is this when S1, S2, S3 the upper four switches are on, then you get VDC by 2. Okay. And when any other these switches or three are on, any three are on, you get plus VDC by 2 in the upper. And lower any three are on, you get minus VDC, and all other space state you get 0. Okay. Now, this flying capacitor multi-level inverter is you can it is the independent of the number of output voltage, and this is more the biggest problem is that you have excessive number of flying capacitors. The capacitor has its own point. So in the according to IEEE standard, for 100 ampere of current, you must use 1000 no, 1 ampere, 100 micro. Yes, 1 ampere current. If your load requirement 1 ampere current, you must put 100 microfarad capacitor. Accordingly, the capacitors are calculated. So one of the paper we sent the transaction paper, they asked that you have put 3300 microfarad where your load current is only 5 ampere. So how do you justify your capacitors? So like that they ask. Okay, so that is what it is. So there's as the number of level increase, it's very difficult to charge all the capacitor, and if there is a some simple short circuit, all the capacitor will discharge. So it requires the you need to put each capacitor should charge with an a rectifier circuit or by a battery source. So then cascaded multi-level converter, you can see that this is three-level cascaded means each are one H bridge, full single phase, one H bridge inverter. There are three H bridge inverters and three capacitors. And this also you need to charge initially. And when you have your switches are on, S1, S2 are on, you get plus VDC by 2. Okay. And then it is connected here. Okay. And when these two switches are on, plus VDC by 2, this. So each point, if you see here, you get plus VDC by 2 and all other point in other, all others may be not proper, is not connected to. So this is what, when you connect here R, when this S1, S2 are on, so you get plus VDC. And that time, S4 or S, S4 is on, so you get 0 voltage here, and S4 here, SC4 is on, you get 0. So VDC, you get 0, 0 from here. So add to this voltage, you will have a VDC by 2. So similarly, this is has needed the separate DC sources you require, which is very difficult. In the if you have a number of levels increase, a number of charging you need require separate DC sources, which is very difficult. But it is the multiple winding transformers are needed because you have so many DC supplies. They all must be isolated. And any device in power electronics we do, that must be isolated. Required less number of devices to rely M level inverter, modular structure, result in high reliability, because as soon as it is not working, so as soon as it is not working, you just replace that full bridge, remove it and put it another one. That is what modular structure. And then separate DC sources are needed, so regeneration is not possible, because regen to drive, you will feed back the power to the source, and that time your DC sources are distributed. If you feedback to one converter, other two diode, one capacitor will overcharge, other two will become undercharged. So that is why this is another problem with this cascaded multi-level. So this is also another cascaded N-level converter you can realize also. So this way we get the cascaded inverter. Okay, this is what, if you add each level from each device, you will see that it is a simple case sine wave. Okay, this is cascaded output. Okay. Now this is also the cascaded connection of UP back to back cascaded connection up. So in the simulation I have given back to back converter simulation also. If two, one inverter and converter both are connected, or AC DC, and DC AC converter is connected to a load. So this is similar kind of that one. So then there are a modulation index, modulation algorithm, like we have a PWM techniques. In case of voltage source inverter, we have studied in our BTech, we studied the hysteresis control, we studied sinusoidal pulse width modulation, we studied single pulse width modulation, we studied multi-pulse width modulation, then SPWM, sinusoidal pulse width modulation. So these are the different switching algorithm or switching technique used for the inverter circuit. So similarly, for multi-level also we need to understand what are the switching techniques. There are all these things like advanced switching technique, like hysteresis current control. Okay, I think all of you must be knowing hysteresis. Last class also we studied little bit about hysteresis current control. When you are comparing to actual current and the reference current, and passing through some kind of controller, you get the output voltage. So that is the hysteresis. And then harmonic elimination method also we studied, and we studied sinusoidal pulse width modulation technique. So, but here we will limit it to sinusoidal pulse width modulation technique and the hysteresis current control technique. That too we will study here a little bit. And that is why when you have a what must be requirement for the modulation? Modulation means you need to have low total harmony. For example, in case of a square wave, for example, this is a square wave. Okay. And if you plot this one, you have a fundamental, first one, and then third harmonic, then fifth harmonic, and seventh harmonic. So third harmonic, what it does, if you see, if your induction motor is developing a torque TL or TE developed torque, if this is the torque, and due to third harmony, another torque will generate, which will be lower in the magnitude, but it will be in the opposite direction. Sixth, again similar direction. So if you see this, the net torque generated by the induction motor is the developed torque by fundamental minus developed torque by this harmonic component. So net torque becomes lower as compared to this one. That is why you see this for this region what we use PWM technique. So PWM technique, so what is the PWM technique? PWM technique means it came, I told already in your class in BTech, I in the code, that initially this PWM technique was initially designed for the digital communication. So when initially the data were transferred from one place to another place, if you have a bulk amount of power and it is analog signal, it is the analog signal is always associated with the electromagnetic interference. And in our childhood, we have seen there was the telephone lines. In the telephone line, always they go near the power line because the power supply which is used in the base station is connected from the power supply from the power line. That is why it was. So due to that, there is a lot of interference and signal to noise ratio. It was very high. So then people thought of discretizing a small packet you divide, and in this packet you send it. So that is what the communication started. They are rethinking that how to make it digitally possible. So how to do? Initially, they design a sample hold circuit. Sample hold means the sampling means 1 kilohertz, like you have a big maybe one big brinjal, okay, or you cut into pieces. A big brinjal you put in the oil or put in the, it requires a lot of time to fry or this. When you big brinjal you cut into pieces and easily you can fry in the pan very quickly by put little oil and fry. Exactly similarly, this communication also, they used to send all the bulk amount, then they cut it once, and that was called the sampling. They cut that one, and then because you are doing cutting like this, so all this sampling or when you cut it, it depends on the speed of your hand, and sometimes a very big amount will cut, and sometimes very small, thin, sometimes big. So there is no uniformity and the sample and then the whole circuit is to create again that continuous signal after the sampling. So this sample, when this sample was not properly because of these so many things, then we decided that no, that should be the sampling time must be fixed and it should only cut all the packets must be same length, same size, same byte or whatever you are telling in the digital domain. You can say whatever it may be. So we thought that it should be very small, and it should cut into that one. So that way, they have started comparing a sawtooth wave with a reference wave, and then according to that frequency, they switched on. And that technique we took, that is called pulse width modulation technique. And when you have then they understand that they try to find out what is the autocorrelation, what is cross correlation. Those in the communication theory, if you go through that one, lot of things are there. So then they decide they started delta modulation. After delta modulation, there are many techniques you can go through the communication system. I'm not going detailed. Then a sinusoidal pulse width modulation, and we used to have the sawtooth. In the sawtooth, our synchronization has many problems actually. So that's why the sinusoidal pulse width modulation became very popular. So sine wave and a triangular wave we compare. So by comparing that one, what we do, because the triangular wave is very high frequency, 10 kilohertz, 5 kilohertz, and compared with the sine wave, and you switch on that way. So what happened? You have a fundamental. Then the next harmonic will be the M or the order will be, order means according to frequency modulation. The F of the carrier divided by F of the reference wave. The reference wave is 50 hertz and F of carrier is 5 kilohertz, 10 kilohertz. So you will get a order of this one, 11th. So you will see that your frequency, this harmonic is shifted at 11th time or 21th order. So that means what it is shifted from the lower harmonic component. In lower harmonic component, you require very big inductor capacitors, and when you go to the lower or higher order harmonic, easily your line is having inductor. That inductor will filter. You don't require any filter. That is what this pulse width modulation technique becomes very popular in the power distribution, even industrial applications. Okay, so that way low switching loss and less complexity, because designing a, I remember my guide gave me to design a sinusoidal PWM technique by using OPAM only, and then hysteresis current controller by using OPAM. So I started designing, and you see that when you design they like that complexity, the circuit became so complicated. Three means you required two capacitor comparator, then lockout circuit, then you put again the driver circuit. If the signal strength is not there, again you put a buffer. This became very complicated if you actually design in hardware. It became very complicated, and such thing you cannot debug easily. When this hardware system, you cannot easily debug like you do in your simulation or this one. That is why the complexity and circuit layout must be very important factor here. Okay. So this way, there are different advanced technique modulation strategies in phase PWM, phase opposition, space vector, selected harmonic elimination, and third harmonic. So these are the advanced technique which we use. So we will see these three, okay, and these two you can read. Okay, it is extension of this one. Okay, this third harmonic injection is extension of this one, and this is selected harmonic. I already told you, fifth harmonic, seventh harmonic. So anyway, this is. I don't think that today it is possible to finish. Okay. Anyway, this. Uh, then this how to switch on the PWM technique we have already studied. We have in phase means both the reference waveform, they both are in same phase. Okay, so this is, that is what I call in phase. Okay, SPWM. So two carrier wave, one is upper one, another one lower carrier, and it is compared with a sine wave. Okay, and when this is compared, when VR is greater than VT, so you get this one. So this, you can see that when VR is greater than VT, you get a pulse here. You get a pulse here. You get a pulse here. Okay. In negative cycle, you can see that here you got a pulse. Okay. So this way you can compare for a 3 level. Okay. If you require 5 level, you will have 4 offset carrier waves. Okay. You require, and that is way. This is the same way we have. So this is our the line to line voltage. You can see that these are the line to line voltages. Okay, 1, 2, 3, 3 level. And this way, phase opposition also, because in the phase opposition, the difference is that this carrier wave and this is opposite in phase. Okay, so this is called phase opposition, and this is these are the in phase opposition. This is the hardware result what we did. So anyway, these are the uh, total harmonic distortion, THDF, voltage and current. So then there is another technique called the dipolar PWM. In the dipolar PWM, you can see that you have one carrier wave moves from here to here, and but you have two reference waveform. You have two reference. One is here. This one is your reference. This one, two reference. And the same logic you apply and you get the output voltage like this. Okay. So this way, and this is the third harmonic injection. Injection means I inject. This is your sine wave. When you apply a third harmonic like this is a third harmonic. Okay, component. Oh, sorry. So when you have injected third harmonic into this system, okay, this is a third harmonic component. Nah, like this. This is third harmonic. When this one you inject here in the sine wave, what you get? Here you get more, and then at this point it is minus. So this is reduced from here. So you come down again this. And why this technique used? This technique used because you see the width of the sinusoidal is increased here. If you see here, the width is from here to here increased. But in your sine wave, it was from here to here. That is why DC utilization became very high here. So this is what you can, these are the features. And then space vector modulation technique, and similarly you can have a space. There are 19 effective vectors and there are 0 voltage vectors. You can see that these are the 0 voltage vectors, and these are the medium voltage vectors. These are the medium voltage vectors. Okay, so these are the medium. This is full. This is half medium. So these voltage vectors are chosen accordingly. So this way we can choose, and that way we can get. Anyway, so uh, we should stop here. So maybe next class I'll continue this one. After finishing this one, then I will discuss in the blackboard. So all of you can write down. So when I will discuss, so I will start with the reactive power of an uncompensated line. I think transmission line fundamental all of you must be knowing, or else we will also just go through a few equations of transmission line like ABCD parameter, everything. And then we will study the compensator, uncompensated line. Then we will go towards fundamentals of phase controller. Okay? So with this, we stop here. If you have any questions or comment, I can. Uh, okay, then if there is no question, we will stop here. Okay.